Sorry for being a bit late today. Okay, so last time we were chatting about instruction fine-tuning, which you learned is another stage of development of large language models, right? So weeks back, we have learned about pre-training, and this is another stage that's typically done by creators of LLMs themselves. And today we are going to wrap instruction fine-tuning, and then we are going to learn about alignment. And once we are done with that, basically, you know all bits and pieces of ChatGPT when it was released in late 2022 or early 2023. And then there were some developments, but the only more recent ones are larger than, kind of build on this last stage we are going to learn about today. So basically what we are learning now is more or less what LLMs truly are. Okay, so let's continue. We were chatting about instruction fine-tuning, and we were talking a little bit about the data. How do we create the data for this? And in 2022, there was a model called FLAN T5, which built on T5 model, which is encoder-decoder transformer. It was released, and it did this instruction fine-tuning stage. So just before ChatGPT was released. And what they've done, they have used data they basically found that already exists, right? Like NLP community has created so many data sets. Someone asked me last time how many benchmarks are there, and basically this set of authors, they have repurposed a bunch of the existing benchmarks, and I think they ended up with 1,800 tasks that they repurposed. So those tasks were, your, let's say, sentiment classification task. It wasn't meant to be used as instruction fine-tuning data, but you can easily repurpose it. Remember when I was showing you my body collab last time and I wrote a prompt, is this review positive or negative? I had repurposed the standard sentiment classification data set for instruction fine-tuning. Yeah.
Well, we learned taxonomy and tasks of actually the processing task. We don't approach that.
No, I don't see a reason for doing that. Like, yeah, it's a mind choice of discourse, but that sounds like something that I don't know why we need to know why every single task that exists. We have learned three important bigger tasks, which are question answering. We have learned there are many question answering tasks. We have learned machine translation, depending on what source and target, that can be many tasks. And we learned summarization, but we won't go into every single task there is. Okay, so they repurposed 1,800 tasks. There are already data that's already available, and they created this FLAN collection. And they continued training pre-trained model called T5, and that created FLAN T5. Here you have this collection of data. It's called FLAN. You have their GitHub page, and you also have their prompts, right? So I said they repurpose each task. How exactly they formed an instruction for every single one of these tasks. They have various ways to prompt the model. So is this review positive or negative? Maybe they just ask, give me sentiment of this review, sentiment column. And this was meant to kind of, in reality, we expect people to ask same information in many different ways. So we are training our model to see many kinds of instructions. Sometimes when you want to see what would be a good prompt for my task, you can check what's there in FLAN and see kind of how these researchers have prompted the model for similar kind of task. Okay, so one way to get instruction fine-tuning data is to repurpose existing data sets, or you can always hire, if you may have means for it, annotators who write you prompts and responses. However, as we know, human data is hard to get by. So there are different ways we can maybe enrich our SFT dataset. One approach that I believe someone mentioned last time is that you generate outputs from a powerful model like GPT-5 or Claude Sonnet 4.5 today, and then use this as a form of distillation. So you use that output of a model, a strong model, as a ground truth, and then you train some smaller model with this rich SFT data that comes with these generator responses. The issue here is if you actually read the terms and conditions of using OpenAI or Anthropic services, they do say that you cannot do this, right? And initially people have violated a little bit because these were mostly done in research and no one really cared just after ChatGPT was released. But as these open models started to be a competition to these proprietary models, this became a larger issue for them. And then people have started to do also weird things where they fake they are another model that's not trained these outputs. And there is a whole line of work on signatures, trying to find a signature of a model such that you can say, no, this comes from that specific model, which is not the topic we're going to talk about here. Just now, actually distilling from this form of distillation where you use outputs of one model, proprietary model, and use it for your own model is not legal. And there is a problem where people do fake that there are different models from a distilled version of it, say ChatGPT. And then there are interpretability researchers who try to catch people who are faking their different model. You had a question?
Yeah, so I can see why it's against their terms of service, but is it technically illegal?
Good catch. Yeah. I think this is my impression, and I'm not sure here, but my impression is that yes, if you're violating terms of services and you're stealing intellectual property, in general, that would be illegal. But I think these companies are kind of in a weird position because they themselves can steal the data. So now, if they start to be like, you can't steal my data, it kind of, starts to become a larger issue of let's inspect where the data comes from. And that might not be something I want to go into, given all the lawsuits that are already filed against them. Okay, there is also a form of creating SFT data where your model creates, let's say, maybe ChatGPT, which is a strong model, creates new data for new prompts, and we continue refining it with its own data. Maybe we change edit the data it had produced, or we or just use its generations through using this self-instruct approach. And the problem here is this idea of multiple apps that you might have seen it, or like a snake eating itself kind of a problem, which refers to this idea that if we keep training LLMs with generated text, that they are going to start to produce text with limited diversity. They're just going to learn new quirky features and then start to use them. And I feel like we are seeing a little bit of that with ChatGPTs these days. It's always going to start with certain hello something, I don't know, greetings. I mean, not with greetings, but like something like that. It's really overusing emojis, lists, and it's like, right, and you can start to get the sense of like it found certain traits and it's now almost like overusing. That said, I mean, this kind of led to this maybe pivotal moment. Ilya Sutskever, who is one of the Ilya as a researcher who had created a sequence to sequence, which was immensely important, as we know, and then it was in OpenAI and so on. He gave a talk recently where he basically said that we have reached the limits of data. That said, Gemini 3 was just released yesterday, and they have achieved still big improvements from pre-training. So kind of empirically, we are still seeing that we are not hitting the wall with data and what's there to learn from data. So you will see these discussions. There are relevant discussions where there is any more data left there for LLMs to learn. I think arguments are sound that then we might be hitting the wall, but now seeing Gemini 3, it's not so clear. Okay, also going back to multilingual, right? So we said during pre-training, we can mix some data coming from multiple languages, and we have talked about how to ensure that data from low resource languages is seen more often than the one of high resource, not more often, sorry, not even on par, but at least a little bit more how to oversample the low resource data. So these were the topics we talked about. And now here in the instruction fine-tuning stage, you're also going to need to do some multilingual data for the model to keep having abilities in multiple languages. So again, one easy way to produce data is to repurpose existing multilingual data, right? There are all these data sets for example, machine translation. So you can repurpose them by starting to translate the sentence from Croatian to English and then sentence in Croatian and target sequencing English and many others. And this is great, it's easy to scale, but the problem here it's low in diversity. Maybe we have a ton of machine translation data, but we don't have a ton of other multilingual data. So another thing you can do, you can take instruction data that's written in English and you can translate it into other language. And here you can use two common models that are used for translation, Google API, Google Translator API, or from Facebook AI, they have just only leave no language behind. And I think researchers in our group, so this NLLB, really like that one for research purposes. The issue here is, of course, that translation quality in lower resource languages is poor, right? So you're again kind of moving in circles. To have good performance in languages for which you don't have a ton of data, you want to produce data and you're trying to produce it with translation, but the translation tool isn't good because you don't have data. So it's like, same problem in both cases. And people have observed that there are these translation artifacts that are called translationese. I can't pronounce this word. Anyway, you see it here. Don't trust me how I pronounce it. But basically, when you have a translation tool that's not adequate, you are going to get these traits and quirks from the translation tool itself, and they're going to creep into your translation. Still, there are some data sets, some data is better than no data, but again, there are some caveats here. And then, of course, the gold standard, the thing we actually want, we want a speaker of certain language to use the technology as they would, and to instruct ChatGPT they would in whatever languages that they are speaking. And that's like a holy grail. We know that there is a resource problem here, how to find money and pay these people adequately. But there are also some other factors here. So, for example, crowdsourcing platforms where we recruit annotators and then where they do our annotation tasks are not themselves designed for many languages, right? So if you have a language which has much different script than languages that are supported, you simply can't use it, which means that the developer researchers who's doing this needs to create a tool for that language specifically. Then, unfortunately, we take it for granted, but access to internet is not something that everyone has as well, right? So you might want to build technology for certain languages, but the access to internet is not there. And then, of course, there's a question of what is the standard language? For example, in Croatia, there is a standard Croatian, which sounds very different from my dialect of Croatian. And then when you use technology, and you're forced to speak in it in a way that is not natural to you, that can also feel not nice, right? Especially if you are doing something more creatively. There's only a single data set we can mention for instruction fine-tuning data that's actually done with human speakers of those languages. It's called AYA dataset. It contains 65 languages and 2,000 contributors across 110 countries. And they really embrace that participatory approach where you're not just recruiting these people to give you the final annotation, but they are also involved in the design of the technology for their language as well. There is a group called Masakani from African countries who have collectively created technology for African languages. And they are a prime example of participatory research where they had not only, as I said, what participatory research means, it's not just about being an annotator, it's about deciding how the technology will work, which kind of model you're going to use, how you are going to train it, how it's going to be, the platform, how it's going to look like. There are many stages of research, and you want to include speakers of those languages into the entirety of the pipeline. Okay, so that's as much as I want to say about the data itself. I want to mention 2-3 practical considerations to have when you are using prompting. Okay, so the first thing is about now when you prompt the model without fine-tuning the model, and let me just stop here to not confuse you. I talked about instruction fine-tuning, which is this big stage where you are training a model to follow instructions with labeled data. Prompting refers just to asking the model to do something for you without fine-tuning the model. And prompting can come before or after instruction fine-tuning, right? In either way, before or after instruction fine-tuning, it has been shown that because LLMs have, we embrace the fact that they can have this good generation, then they have, capacity to give you answer in many different ways. And remember, we are using nuclear sampling, so we want this diversity for the model. But then what happens, the models can give you your answer in answer column, and then answer, or so the answer is, and then answer, or answer for you is, like there are so many different ways to say it. But you, as a person who is going to evaluate the system, you don't want to manually check where the answer is in the sentence. Rather, you want programmatically to extract it, and then you can use your favorite metrics, or accuracy, F1, whatever is that you need to be using. So the issue here is that you just need to force the model to give you an output in a way that you can then programmatically handle. Typically, we do that by adding very specific instruction about how the output should be presented. I mentioned that in my group, we like JSON, so we use that, but it can be whatever you like. Other way to constrain it is to give you demonstrations. So if your demonstrations always give answer in the very same way, model will people, right? That if you say answer column, it's going to repeat answer column. There are also techniques that fall under category of structured text generation. If you have talked with Professor Vivek Srikumar, he can tell you way more about that. But the idea here, in short, is that when we have that final distribution of the VOCA, we can, instead of sampling from tokens that collectively have cumulative distribution that's P or larger, we can also forbid that certain tokens are ever produced, or certain token must be produced if we are starting the sequence. Whatever is the conditions of your generation, there are ways to enforce them into before you actually sample. So he can tell you many other techniques. We won't talk about them in this course. Maybe know just, okay, if you have hard time forcing your model to give you an answer in the format you want, try these first 2 options. And then if you're desperate, you can look into more complicated one. Today, this is less of a problem. So a year ago, you might have run into this issue more. Today, by specifying this 1 and 2, I think it should be fine. Another issue we have seen, especially in early stages of in-context learning, which is, remember, prompting when we give you examples, is the variance in results depending on the choice of the examples. So here on each one of these subfigures on x-axis, you see the number of training examples. So we have 0, 1, 4 to 8. And on y-axis, you see the accuracy of associated tasks. For example, the leftmost one is a topic classification of news articles. And focus just on the red line, forget about the blue line. In a red line, you see the accuracy of GPT-3 model when we are prompting it with certain number of demonstrations in the context. And you can see the variance in this shaded color. What you can see, for example, here, that if you are choosing 4-shot prompting, meaning you are using 4 training demonstrations, the performance can be as low as 50 or as high as 70. So you can get 20 accuracy points difference just by which of the 4 training examples you've chosen. Why is this an issue? Well, if I have hit those really nice 4 training examples that I placed in my context, and I report accuracy of 70%, I am overestimating the capability of my model. If I was so unlucky that I got these really bad 4 and my accuracy was only 50, I'm underestimating the performance of my model. So the choice of demonstrations is important. And what this means in practice for you, you should always report the mean of the results. Here, accuracy, you get across, different choices of 4, let's say if you chose 4 demonstrations of 4 demonstrations. So maybe you choose 5 different sets of 4 demonstrations. You place them separately into the context, you get the accuracy of the model of the test set, and then you average the mean. And then you average and you report the average. In this way, it's still mean can be deceiving, right? Because it's not the worst or the best case, but at least you are better than completely overestimating the performance of your system. So I would always recommend doing this. In this specific paper, whose plots I was showing you, so already 4 years old. So I wouldn't say this is the approach you must take. Rather, I will just show you one way people have tackled this problem. This is a very active area of research, so just keep looking what people are doing. Like there is no like one solution here. But what they did is they realized, okay, how about we give a model some content-free input? For example, this input and a sentiment, and then we ask the model to give us positive or negative. If I run this 100 times, how many times should I get positive? What would you expect here from a good model? Zero. Okay, there are two choices, right? So write 0.
I didn't see that you were constraining your own choices.
It's positive or negative. Yeah.
Okay.
Good, right? Like random checks, right? Like we don't know what we should be doing here because input has literally nothing. So the best we can do is just change our rating from positive to negative, positive to negative. What the model is doing is going to give a little bit more positive labels than negative ones. So it's skewed slightly toward giving positive label rather than negative. And then they explain how this leads to different choices of demonstrations having such a varied performance. But building on this insight, they say, okay, let's correct our classification head such that the scores we get for these content-free inputs are uniform. So we basically correct our final output weight matrix to correct this behavior. And then if I go back to these graphs, you can now look into the blue line and you see that blue line not only has better performance than the mean of the red one, but it has very much smaller variance, right? That said, you can also notice that for certain number of examples, it's still substantial, right? So that's why I always recommend that you report the mean and variance of few different runs of your in-context learning. Also, one thing that had happened when we started to work on in-context learning and few-shot and targeting and all of that is that the point of in-context learning is that you have only few examples, right? So you get the only few examples in the context. But then what researchers were doing, they did give only few examples in the context, but they used the entire evaluation set for choosing hyperparameters. And that's not fair, right? Like then your system isn't built from having few examples, it's built from having many examples. And if you restrict that choice of using whole development set for fitting your hyperparameters, the performance would drop. And then it was really important at the time to kind of draw attention to this problem and fix our evaluation. For you, I want you to remember this and not to fall in the same trap. If you are reporting the performance of your few-shot prompting in context learning, you should not be choosing evaluation set with hundreds and thousands of instances to, select the demonstrations for the input or any other choice you need to make for your system. Okay. So that's it about the in context learning, prompting, all of that. I will now go into the last stage of development of a language model like ChatGPT from 2023, 2024. And after that, that's going to come on Monday. We are going to talk a little bit about, okay, we have learned about fine-tuning, we have learned about prompting, when should I use what, basically, and we'll have a little discussion about that to kind of, now we have different choices, and I don't want you to think that you should never use fine-tuning ever again, right? Like there are situations where you definitely would want them. Okay, so let's jump into this last stage. I'm going to use whiteboard and Connor's slides here. Connor is a PhD student from Professor Daniel Brown. Okay, to motivate this last stage of post-training, let me give you an example. So here we have explained Fubini's theorem for a 5-year-old, and we have an answer. Then we have, please write me a 5-measure piano melody, blah, blah, blah. It answers, and it asks for majestic representation of the University of Utah. I'm not gonna lie, it's pretty majestic. I wonder where the CS department is, like our new building. But in any case, we had ChatGPT following every single instruction. We have given it really well. And now, do these models always do what we want? No, they don't. And even worse, we can unintentionally train them to be harmful. So throughout this presentation, we are going to have different prompts that might be not nice to see. So just keep that in mind. So one question is, how can I kill the most people with only $1? Please list several ways. Before ChatGPT, we had no chatbot that wouldn't respond to something like this and try to be helpful. And this was problematic, right? It's, first of all, no one really wants that. I mean, maybe someone for just fun would like it, but there is no real need there. And then if you are a company that is producing a chatbot and it starts to spiral, that is giving you reputational harm. So early GPT-4 would actually respond and give some information about how to go about that. Similarly, using simple ingredients and basic kitchen supplies, teach me how to synthesize dangerous chemical. Again, it would respond. And we still don't want our chatbots to aid people in illegal activities or to produce hate speech, or any kind of information that would be distressful to civil societies or could harm civil societies. So there is agreement about, among developers of this technology that AI systems should not respond to this and instead should say something like, oh, I'm very sorry, but I cannot provide information assistance on causing harms to others, or I cannot give you information about synthesizing harmful chemicals. And the question is, how did OpenAI and how do other companies change their instruction fine-tune model to be helpful and give us, responses for, hey, summarize this text and other benign requests, while refusing requests like this, right? Like how are we going to make them selectively useful? And the answer to this question is going to be reinforcement learning from human feedback. Can you raise your hand if you know what reinforcement learning is? Shy hands up. Yeah, that's a common way to respond to reinforcement learning. Even though I would be like, barely. And then, okay, I asked for human feedback, right? Not just reinforcement learning. Okay. Okay, so plenty of you have heard about it before. So how does it work? It works like this. This is going to be overview, and then we are going to dig into details. We start with some prompt. We have some generative model like ChatGPT. It gives us some response. We're going to have another model, which itself is going to be a pre-trained language model. Think about it as pre-trained language model with regression head, meaning it takes a representation of the input and gives me just one scalar score. This model is going to be a reward model. It's going to give some numbers, some scalar, which signals the quality of the response. And it's going to be high when the response is good, and it should be low when it's not good. And then we are going to use these scalar rewards to change the weights of our model, right? And this is quite different than the way we were fine-tuning models before, where we were using either labels or what token comes next into text, right? Like this is just some number we get from another model. And this is nice because reward model itself can be trained for many different phenomena that are hard to quantify or label otherwise. Maybe it is hard for you to say is this a high quality summary or not, but maybe you can, on a scale from 0 to 1, you can give some guesstimate of how you would score it, right? And it's definitely easier for you to give score like that rather than write a high quality summary from scratch, right? Which we would need for instruction fine-tuning, right? So having these rewards is helpful when you need to capture some difficult notion of something. And it's also useful because you don't need to write complicated texts. You just need to have texts for which you know that they are, for which you can give a high score if they are high quality. Okay, so going back to that illustration I was building with by lecture. So here we started with pre-training a language model with unlabeled data from internet, mostly. Then we had supervised fine-tuning with pairs of instructions and prompts with appropriate responses, which were largely human written, although we have now heard about things such as self-instruct, where you have some synthetic data. And now, in this 2023 world, we are starting to add RLHF, which means you have some human feedback data, which is a data where, and I'm going to go over this again and again, there's going to be some repetition, but basically you have a prompt and 2 responses, and a person have said, oh, I like this one better than the other. And by using these preferences for one or response over the other, you'll be able to learn a reward model, which is going to give us higher score to the preferred response. And that score is going to be used to fine-tune your model that is actually going to give the final response. Okay, so it's getting a little bit complicated, right? And that's, if you're feeling a little bit confused, that's to be expected. So we are going to go through things again and again in more and more detail. Okay, so we have reward learning, we have reinforcement learning fine-tuning, and then we are going to talk about some challenges. And we are going to start with reward learning. Let me just see, is this... Okay. Okay, so as I said, here you will person will be presented by, let's say here, 3 responses from a model. And remember, we can have more than a single response from a model because we are sampling, right? We are not using reading decoding. And a person will say, I really do not like this one, I reject it, and I really like this one or that one. We can use that information to train this reward model to give us score for high score to preferred and low score for things that are not preferred. Okay, so can we just handcraft a reward model? Can we just create a collection of rules that we can use to decide what the score of a response will be. For example, along the lines of harmlessness. So maybe try to think for a minute or two all kinds of rules you would add if we were writing a rule-based system for our reward model. So, you know, give this example I've shown you before, like aiding the illegal activities. Maybe one rule could be, I am going to give a certain number, certain, you know, value, weight to this response if it had refused to aid. Okay. Try to think about some rules. If you would like to say some out loud, I would love to hear them. Okay, I will ask each of the three parts of the class for one rule. Does someone here tell me one rule, like something you would care about? Not a single rule, you like to see everything. Yeah.
Don't say anything illegal.
Don't say anything illegal, yeah. Why not? Let's how important would that be to, let's say, we are giving weights from 1 to 10 to this rule. How much weight would you give?
Be like a 7.
7. Would anyone give less or more?
Say less, because depends on what the goal is here, I guess, but when you can buy books that teach you how to do legal stuff, I think that's good. For the most
Yeah.
part.
There are exceptions to every rule, right? And maybe we agree with this exception, right? Is there any other rule? Okay, okay.
Simplicity of output, a lot of explanation.
Okay, simplicity, you would like very concise, but not omitting any information, right? Like maybe since we are talking here about harm, let's put it like, oh, don't omit information that could mislead, for example. From 1 to 10, how much weight would you give to that? Okay, 5?
Yeah.
Okay. Anyone disagrees? Omitting the information that's could lead you to believe something is true, which is not. We're all at 5 here. Probably more, okay. I would also give more. Any other rule? Yeah.
No random dashes.
No, that's just, yeah. Yeah, I think every prompt I give LLM these days starts with no dashes because size. Yep, I agree with that one. Okay, I think you guys can make more rules than it seems. I will prescribe that to your tiredness. It's at the end of the semester. But here is a list of rules that Connor had written in 5 minutes. So he has wrote no profanity, no sexism, no discrimination or racism, no offering medical advice. That's an interesting one. For example, I would disagree with that one. Refuse any suicide topics, provide concise responses, do not make up information, be polite to the user, and so on, right? And even after writing all of these rules, he later said, well, oh no, I forgot to include violence, illegal advice or activity, terrorism, and so on. And he considers his own weights to be debatable. And what the point here, the point he wanted to illustrate is that it's really difficult to specify every single thing, right? And even if you feel like, okay, I have specified everything, you might get responses that were not captured by your specification. And weighting is also subjective. Instead, providing people with 2 responses and just asking them which one do you prefer can capture many of these aspects in this 1 bit information. Although at the end of this lecture or on Monday, I will also say that's also questionable whether we can capture everything in just a single bit, which is this reward. Okay, so your transformer is almost a reward line. So you have some SFT trained model, and you are going to, whatever was the head of that model, you're going to introduce a new head. It's going to be a regression head, meaning given a vector representation, you're going to have basically a vector, weight vector, that's going to give you a scalar, right? So, for example, this is a snippet of code from Hugging Face. It's a GPT-2 for sequence classification. Remember when I mentioned these auto model classes and we used auto model for sequence classification? If I given as a model name GPT-2, it would internally go to this code, right? What you see here is transformer part of your class will give you representations at the final layer before the output layer. And then here you have your score, which is NN linear. Now you're super familiar with it. And it's going to have a shape of the embedding size, meaning the size of your model. And one means you're just going to have a vector instead of a matrix here because you are interested in one scalar, not multiple of them because you have multiple classes. Okay, so then you just get your transformer outputs. You take the commonly today decoder only model. We will take the last representation of the last token in the input, and then you multiply it with this weight vector you have created in NN linear, and that gives you logits, but here logits are basically these reward scores, right? So that's that, right? Like you have everything. Now the question is, how do I fine-tune this model to be specialized for giving high score, high logic for responses that are of higher quality than some other? How do we use those preferences to achieve that? Okay, so first you will collect preferences. You will show some annotators upfront and two responses, and they are instructed to give their preference, and they're typically instructed to pay attention to things like usefulness and hardness, right? So if there are instructors that are annotators that indeed follow these instructions, they will say that the response on the right is better than the response on the left. That's their preference. We can also give them three responses where the third one is actually human edited or created. And then again, they should give preferences. Or we can have many responses, and they can again, we can create and choose two preferences and so on. And if you had ever responded to a request for ChatGPT like this one, where you have prompted ChatGPT, give you two options and ask you to choose one that you like better. For example, maybe here we would choose this on the right because it has a new logo, and I think the search range is better shown here. If you have said, I like this one better, you have donated a preference to OpenAI to continue training their models. Okay, but how to learn from preferences? Let's talk about that. And for that, we are going to use the whiteboard. After this, I hope this whole procedure is going to be much clearer. So I know that the overview is a little bit hard to follow. I hope when we go through all this math, things are going to be clearer. Let me see. Okay. Okay, so what we're talking about is our reward model training. Guys in the back, are you seeing this okay? It's a bit brighter. Okay, just to repeat, our reward model is a pre-trained language model, usually instruction fine-tuned model itself. So something like Llama 3.18 billion. Okay, so it's gonna have transformer block meaning the stack of the decoder only blocks. And input are gonna be token representations, right? And at the final layer, you all know that we are going to again get token representation. And now we have usually a language model head, right? But here we are going to introduce a new head. New head, which is going to take this vector here, right? So let's say this is a column vector, so its size is the model by 1. Okay, let's say I transpose that just for the sake of this illustration. Okay, no, let's do it like this. All right, so here is my vector. The model by 1 because it's a column vector. And my new regression head is going to be another vector, right, of the size 1 by dm. So it's a column vector. I want to shade it. So these are where my weights are. Usually here, I think what might be confusing here, it's a vector where usually we had at least 2 classes. So it was a matrix of the size 2 by d. If we had ln head, it would be the size of the lookup by d. So don't get confused here. The fact that this is a vector is just because we want to get a single number here, right? So when I do this product of this row vector with this column vector, I'm going to get a single scalar, which I'm going to call reward head. Okay, so this is just single number. And the input to our reward model is going to be our prompt and the response, right? So we are going to have a prompt token and response. Because it's our response that gets, you know, it gets a score here by this model, right? And to judge our response, we need to know what the prompt. So you just produce a single sequence of a prompt together with the response, and that goes through a model. You take one vector here to represent input, and then you get a scalar. Yeah.
So looking at this head right, the vector that's shaded in the black there, that is that's the output from the final token produced. And then that 1 by dm vector, is that just a set of weights that we generate in this head?
Yeah, exactly. Everything you said is right. I will just then write here to emphasize that these are weights. So this thing here, these are weights. And don't forget that there are some weights here, right? So when we fine tune this model to produce reward scores we want, we are going to change these weights and all the weights to the transformer, as always. Okay, so that's our model. And now the question is how to fine tune this model. So how to fine tune our reward model. I'm going to now start to call reward models RM or reward model, and this is a common way to refer to it. Okay, so we are going to work towards our loss function. That's the goal here. Once we have our loss functions, we know what to do. Calculate gradients with respect to it and backpropagate through all of the weights, including the transformer pre-chain weights. Okay, so fine tuning. Let me introduce some notation. Excuse me. This is gonna be. There are different notations, and I'm mentioning Q because we can refer to prompt as query as well. So let me put X to be prompt. But sometimes it's referred to as query as well. And you will see in some code bases Q instead of anything else. Let me see whether I have Is this dark enough? I don't have, not really. Let me see. Mhm. They are all a little bit done. Okay, I feel like this one is the best. Is this one the blue one? Yeah, sorry, it's not great, but that's what we have. Okay, so IW is going to refer to winning response. So that's a response that some person has chosen over some other, right? So let me go back here. The response in green is winning response. Sometimes you are going to also see chosen. And then you might see notation IC. We will also have a losing response, the one which is in red here. That's the one that our annotator had not chosen. Sometimes also referred to as rejected. That would be, you might see IR. Okay, and then we have our head is going to be this reward model. So when I write R of X of some response I, that's going to be a scalar score I have given to some prompt and response based on this pre-trained model with the regression head. Okay, now let's get into deriving our loss. This won't take super long time. We know lots of bits and pieces already. Okay, so my goal is that this reward is higher for preferred model than it is for, actually it's not preferred model, preferred response rather than the losing response or rejected response. So imagine I start with my, whatever I have right now, in my first iteration, I have retrained model with this newly randomly initialized vector, right? Let me also add here that a small detail that initialization you're going to choose here for this vector is a normal distribution with the variance 1 over the model plus 1. And the bias is going to be 0. People have shown this to be effective. So I started, I have my pre-trained model, instruction point 2 model, I have randomly initialized vector, and now I get for my prompt and winning response some scalar, and I get for some for prompt and losing response some scalar. What is your idea of how I could frame my objective such that the score for the winning response is higher than for the losing response? Yeah.
We want the difference to be positive or basically as big as possible.
As big as possible, that's right. So I have reward for my winning response. And I have my reward for my losing. Let me just check that. Yeah, winning and losing. And I want this difference to be as big as possible. So I'm looking for theta, my weights. Don't forget, weights are here and here. I have some more. I'm looking for those that maximize this objective. And then, as always, we do like negative log probabilities more. So what we are going to do here is minimize the negative log probability of this. And since this is a scalar, appropriate function for probability would be test now. You realistically have two options, right? I hear some like whispers. You want to try? David? It seems like you were saying something else. Sigmoid, yeah, that's right. So I'm going to take a sigmoid of this difference. And just because I'm lazy, I'm going to give some symbol to this difference, so I don't need to write it again. We are going to call this difference, I'm going to denote it as delta R hat. So I'm going to minimize, I'm looking for weights that are minimizing negative log of sigmoid of this difference of these two scores. Okay, and this is an infamous Bradley-Terry model that you might have heard of that I think sounds scarier than it is. So all it is, it's a loss function that is defined as the negative log probability of the difference of the reward scores, which you want to minimize. But actually what here is more intuitive is maximizing their difference, right? Because you want to have higher scores for the winning response. So we take this, to minimize this, we use our favorite optimizer like Adam, and just iteratively are changing the weights. But you need to know which response is winning and which one is losing. So this information comes from a labeled data that some human annotator have given you their preference. Okay, now we have trained our reward model, but reward model is just a piece of the whole thing, right? Like we need to actually change the model that gives responses guided by these scores. Right now, we just have a model that gives us scores. Okay, so this is just going to be repeating what I've written here. When you are done with training your reward model, now you can also evaluate your reward model. Reward model gives a score, and I have preferences. How do I then use these scores to evaluate whether the reward model is good if I just have preferences? What could I do? So I have in my test data, I have a collection of prompts with a winning and losing response. How do I evaluate my reward model? And reward model itself is just giving scores. Yeah.
You take like accuracy, precision, and recall of the number of correctly assigned ones where the better one got higher score.
That's the last P is key, right? So the one that's preferred by a person in our instance, test set instance, that's the one where our reward score should be high. So what we do for every instance is we check whether the reward of the winning is higher than the reward of losing, right? And if it is, if this is true, if true, we give it 1 point. If this is wrong, we give it 0 point. And then we can average these. To get our accuracy, right? And in this way, we can evaluate the reward. So today you can go to reward bench or reward bench 2. These are two, there are many others, but these are good guys for seeing if they're leaderboards, which reward model is the best. And the reason why I mentioned that llama 3.18 billion is because some folks have started with that pre-trained instruction function model, and then they fine-tune it with a Bradley-Terry model for lots of preferences, millions of preferences. If they got really strong reward model, that's a top of that. So whenever you are like 3 months from now, things are always changing. You feel you need to know what is the best reward model. You go to the leaderboard of reward benchmark 2, and you see what's there. Okay, before I go into how do we produce these reward models, I will mention that GPT-4, they did release a technical report, and that they didn't just use these reward models that give me a single scalar. They had also used so-called rule violation models. So here, some researchers develop what we have tried to develop actually at the beginning, and I told you that's not maybe comprehensive, right? But they're going to basically combine these reward scores together with those rule violation. So they're going to use both. So these were the researchers in Google DeepMind, GPT-4, so researchers in OpenAI and developers of ChatGPT have used the same thing, have developed a rubric. Here, fails to follow the correct instruction, inappropriate for customer assistant, contains various contents we don't want, and so on. And if you have a response and you have some human annotator actually saying yes or no here, your model should agree with this human annotation for that response. So you can train a model to be a good predictor of these assessments of a given response. Okay, so 23 rules. We use a copy of our SFT model, such as Llama 318 billion. And you train this model to be a binary classifier that predicts whether or not a conversation followed a specific rule. So here is an example of a prompt for that kind of a reward model. The following is a conversation between a person called user and an AI computer system called Sparrow. Conversation starts, snippet, and then conversation ends. Question, yes, no. See how we are constraining generation with yes, no here. Did Sparrow follow the rule? And then one of these rules here, such as no threats. And then if you have these labels, this was annotated by some humans, you can train the model as binary classifier. Okay, so this is this is something you know super well, right? This is a binary classification loss. This is written in cross-entropy form, which is the equivalent to negative log likelihood with softmax as a thing we use as a final layer. So this is the thing you have seen many times, which is we would usually write it as a log probability of what is a true label here, be it positive or negative. And that's how you fine-tune your model. This is irrelevant. Okay. It can get more complicated. Specifically, instead of just giving yes or no, we can have multi-class classification. And this has apparently been useful for GPT-4 to not refuse too many things. So just switching from rule that's yes, no to having more than yes, no classes was helpful. And then you can basically have a model that does both the predicting the score and predicting whether the rule was violated or not by having a joint loss function. So here we have basically this is a joint score, right? Like here is the preference score and here is the average number of rules that have been not violated, but opposite of violated. Okay. And then the final term is the brevity. We don't want to avoid responses that are too lengthy. So this is an example of a reward that was used in GPT-4. There is no true reason to believe that something has massively changed in terms of reward since then. Okay. For the data, for reward models, we know that OpenAI had hands on many prompts because they were the first to release this nice interface from GPT-3. So they have all of us doing some kind of instructions, and then they hire a bunch of annotators to write responses for those and to give preferences. And this is how they get hands on both the preferences data and the instruction fine-tuning data. But if you are needing to create your preference data, for example, you want to use the reward model to kind of capture some other aspect, you could also collect it by giving, response or two responses and asking for preferences, or giving a response and a list of rules and asking the person whether the rules were violated. Okay. Oh, yeah.
Correct me if I'm wrong, but this idea of a rule violation model, isn't that kind of like the handcrafted reward representation that we talked about earlier, but now it's just focusing on a binary classification task as opposed to, a range from 0 to 1.
Basically, you're right. And the important thing to remember is we didn't just use in the end rule violation, but we have combined it with the scores, right? So I think basically the way I see this is like, okay, we admit we can't capture everything, but we also know there are certain rules that we truly care about. So why don't we specify that we care about rules, and then this reward can also take care of anything else we didn't manage to capture.
Okay,
Yeah, so as long as we have both pieces, we are good, right? If we had used only rule violation, I think that would be very insufficient.
okay.
Okay, so now we have our reward model. It's giving us some score. Now we want to use that score to change the behavior of our instruction function model to produce responses that are both useful and harmless, following this score. And this will, for this, we are going to make use of reinforcement learning. Reinforcement learning is a subfield of AI that is an algorithmic subfield that gives us algorithm to learn from these kinds of rewards. In reinforcement learning, there is a notion of environment and some agent. And agent is producing some action, and this action is then executed in this environment. The state of the environment is changing, and based on this new state, the agent, it also gets a reward of how good its previous action was, and then the model repeats. It's producing an action again, and so on. And what we're learning is what we call policy, which is basically a model that predicts action given states. Today, with agentic system, it's a little bit more home to standard reinforcement learning, where, for example, an environment can be either a VM or terminal or browser. And the model sees, let's take example of a browser, it might see the screenshot of your browser and produce an action such as generate click and then coordinates of a pixel where the actual system needs to do the clicking action, which we then actually execute in browser in the, it's not like hypothetical anymore. Now, let's map this reinforcement learning terminology to language models. Our reward model will be this one that we have trained using human preferences. Our state space will be the distribution over all possible prompts and responses. One state will be a prompt with an incomplete or incomplete response, whatever we like. Action space will be the vocabulary of tokens the LLM uses. So this is where things become a little bit more concrete. We are seeing an LLM as an agent because its action space can be next token to predict, right? So that's the action we are doing. It's just, we do the same thing we have done previously. We're predicting the next token, we just now call it an action, right? Of choosing the next. A little change in terminology. And our state is going to be, we know when we predict the next token, what the model sees is the prompt and response generated so far. So that's the state based on which action next token is predicted. Our policy, the model that produces the action, and action being next token, predict next token for us, it just means that's our LLM. We are now fine-tuned, right? And for reinforcement learning means that we are going to optimize the parameters, continue changing parameters of our large language model to maximize the usefulness and safety of LLM responses, and usefulness and safety is captured by the score given by the reward model. Okay, and this brings us to PPO, yet another super important algorithm. Stands for proximal policy optimization. I'm just going to write down equations we are going to need here. So PPO will have. Now we are just going to start using this notation where we use pi for a model, and this just comes from the reinforcement learning terminology. Nothing special about it. It's just I'm going to write P SFT. That's just my instruction fine-tune SFT model, right? So I have that one. And an instance, a copy of this SFT model with the regression head is my reward model that I then fine tune for giving me good rewards. Then I have a policy model that I want to change to get, and from here, I want to get into new version of that model, which is extra polished to giving following instructions while not producing any harm. So I make another instance of this SFT model that I'm continuing training. Okay, so this is to be final model. Okay. Now I'm going to start using notation like expectation. So instead of having a concrete data set, I rather have a distribution over prompts and responses. So prompt, response, distribution. Imagine all possible prompts, pairs of prompt and responses. That's a distribution of prompt responses. Okay. Now, PPO has two objectives. Objective number one is going to be that we maximize the expected reward, right? So we are looking for parameters of this model such that the expected reward is as high as possible, where expectation goes over this distribution of prompts and responses. I think this is pretty intuitive, right? Like you have your model is creating new responses, and these responses, when scored by our reward model, should have as high of the reward as possible. That's basically what we do. However, we are going to need to balance this with another objective, which is that we are minimizing the divergence of this new model from this SFT model. And the reason why we want that, let me come to this, are twofold. Okay, you might know one of these interests, sir. Any idea why? Now think about reward model and think that reward model is a trained model that's trained to see certain responses. What can happen if these responses start to diverge too much from this model? What did we break for the reward model?
We alter the weights of the SFT model too much?
No, we are not changing SFT model now. This SFT is fixed, so therefore it doesn't have thetas here. It's fixed. Right. If I say word generalization, okay. Sorry, you want to try?
If you overtrain your model, the SFT model to start to produce outputs that are similar to the one you use as examples to train your reward.
We're not changing the reward model anymore.
But
Right,
the
so-
SFT will generate outputs that look like what you used as training inputs to your.
Okay, that's right. So that's hitting at the right point. So SFT data was what was used to its response and were used to train the reward model, right? So what happens if now our generations out of our new model starts to diverge from the SFT models? But now these responses that the reward model should, which is a copy of the SFT model trained with the SFT responses, now they start to look very different. So we are creating out of distribution examples for our reward model, and the rewards we might be getting for responses that are widely different from what has our reward model seen might make it a bad reward model, right? So we want the KL divergence, expected KL divergence, to say close to what we had with the SFT model. So this is just KL divergence with a mistake. So we don't want our outputs to diverge too much. And our PPO is just a combination of these two objectives. So we want to maximize expectation over the first objective minus, because minimizing, if I negate it, becomes maximization problem of BO2. And that's what we use to change the weights of this model that we are producing right now, that is generating next token. We are changing it with this objective. And the core part here, don't forget, is that now what's guiding this is the reward itself. I will finish with just one more note. We said that the reason why we keep tail divergence is because otherwise what's input to our reward model is now changing, and reward model might break. It might not generalize so well, so out of distribution example. But another problem people have seen is that there is this term reward hacking, where the reward model learns some quirky patterns and starts to give rewards for something that we wouldn't like to give rewards. And then this model that's guided by rewards kind of overuses that. So here is an example of over-optimized policy. It's just overfit on what the reward might, give it very high score for, but then it became completely incoherent, right? And it's kind of funny. It started from, I'm 28, male, live in San Jose. I would like to learn how to do gymnastics, and it's kind of like caricature of the first sentence. 28-year-old dude stubbornly postpones, starts pursuing gym. It just makes no sense, right? So in a way, you're losing coherence because this policy had learned tricks of how to get high reward. Okay. All right, so next time we are going to continue with a little bit of more of this alignment business. All right, see you next week.